There are two general types of bonds that we've covered up until this point in chemistry, which are simplified as ionic and covalent. However, in reality, it isn't that simple. Many of the compounds that we are going to do have bonds that exhibit what we call a gradient between the two, meaning that the bonds are not completely covalent in the sense that they're completely or evenly sharing an electron. However, the electron is also not completely transferred. So there is kind of a middle bond that happens between an ionic and a covalent. So let's further dissect covalent compounds. And in the general sense, in covalent compounds, electrons are shared between elements. Now, how they're shared is what's going to further divide this kind of compound into two. If we say that electrons are shared evenly, okay, then we call that a non-polar covalent compound. And what that means is that the compound itself isn't polarized. Or there's, more specifically, if they're shared evenly, there's an even distribution of charge, okay? Now let's say electrons are shared unevenly, so one atom is more electronegative than the other and is therefore going to pull the electron closer to its valence. Well, if the electrons are shared unevenly, we say that it is a polar covalent compound. And in physics terms, that would be polarized. So there's an uneven distribution of charge. More specifically, we can say that one side is partially negative and the other, the one that is kind of losing its electron, not losing completely like in an ionic bond, but somewhat losing, would be a partial positive. And this weird little shape is the Greek symbol symbolizing that we have a partial charge in effect. So covalent compounds can be polar or non-polar. It really just depends on what the electrons are doing. And polar compounds, which again, the electron isn't transferred, but it's unevenly shared, is going to have properties, right, that are similar to both, you could say, ionic, right, and covalent compounds, because they're really kind of in the middle between the two. So the question is, how can we tell if a covalent compound is polar or ionic? Or if I should say, more specifically, if the bonds in those compounds are polar or non-polar. So the polarity of bonds is based on electronegativities, or I should say electronegativity differences. So we often mark it with this symbol here. Now, how do we really determine if a bond is polar based on electronegativities? Well, it's really based on change in electronegativity ranges. Okay, and there's, in Chem 20 anyway, there's three large ranges that we largely look. And so when the difference in electronegativities between the bonding atoms are between 0.0 and 0.4, we say that this is non-polar covalent. Okay, I'll just write cove here. If the electronegativity differences are between 0.5 and 1.7, then we call this a polar covalent. And then, of course, if it's 1.8 and above, we say that this is really slightly ionic to highly ionic. So there's a range of ionic character, but slightly to highly ionic. Now, there's a couple of exceptions. So, for example, H and F, this has an electronegativity difference of about 0 or 1.8, but it's not ionic. Some people would classify this as slightly ionic, but we know that there's not a metal and a non-metal here. So there are some exceptions, as well as some ionic compounds also fall into this one, like calcium and carbon or calcium carbide. And that one falls within this range, but this one is ionic. So with the few exceptions, we generally like to follow this chart here and refer to it when deciding if things are polar, nonpolar, or ionic. So let's say we're asked to define each bond presented below, A through C, as nonpolar, polar, or ionic. Well, what I've done here in red is I've taken the liberty of putting the electronegativity values that you would find on your periodic table. Now, depending on the periodic table you use, these values will vary slightly. However, you're only expected to use the Alberta Chem 30 data booklet. So we are going to refer to that one. So here I got hydrogen to carbon 2.2 to 2.6. So when I take the difference in electronegativity, and it's an absolute value, so it doesn't really matter whether you go 2.2 minus 2.6, but I go bigger minus smaller always. I end up with a value of 0.4. For the next one here, we'd go 2.6 minus 2.6, give me a value of 0. And then, of course, for the last one here, that'd be 3.4 minus 2.2. And that would leave us with a value of 1.2. Now, what do these mean? Well, this here, although it's, you could say slightly polar because it's not 0, it still falls within the range we stated before, which is 0.0 to 0.4 is going to be nonpolar covalent. So this will be nonpolar. This one is definitely also nonpolar. It's within the 0.0 to 0.4 range. And then this value here is highly polar. Okay, because it is in between 0.5 to 1.7. And so once we decide, right, on whether these bonds are polar, that's going to affect what is happening to the sharing of electrons. So for example, let's say I draw this diagram over here, and I'm drawing the bond from hydrogen to oxygen. And as we already stated, that it is a polar bond. And what that means is the highly electronegative oxygen is going to have its, it's going to have a greater pull on the electron. So the electron from even the hydrogen is going to spend more time around the oxygen. And so what we do is we draw this red arrow over here. This is called a bond dipole. And what that does is it shows the direction. So bonds are vectors, which means they do have direction, but it shows a direction that the electron is pulled towards. Excellent. So we draw an arrow, and that's facing towards the oxygen. And again, the electronegativity values tell us that. Now, we're not done there. Because the electron cloud or the electron area, right, depending if electrons are particles or waves, the electron cloud will spend more time around oxygen. Now, it won't spend completely around the oxygen. It's not a transfer like an ionic bond, but it will drift towards the oxygen. So what we're going to say is that oxygen, because of the electron cloud that is present, it's going to have a partial negative. And that little weird S does mean a partial charge. Okay? And so because the electrons spend more time around the oxygen, it's going to have a partial negative. And because hydrogen almost loses its electron, it's going to have a partial positive. And so we call these two symbols, along with the dipole, that is, or with the bond direction, that shows the true characteristic of a polar covalent bond. So in terms of the overall method and how to do these, the first thing you do is you draw your bond dipole towards the more electronegative atom, which makes sense because that's the one that has a greater pull on the electron, right? And then you place partial charges, partial negative and partial positive wherever it's appropriate. So let's say I take hydrogen and bromine, for example. And hydrogen has electronegativity value of 2.2 and bromine is about 3.0. Well, since this has a higher electronegativity, I'm going to draw the bond dipole towards bromine, thereby making it partial negative, not a full negative. It's not an ionic compound, but partial negative. And since hydrogen almost loses its electron, it'll be partially positive. And this would be the complete bond diagram for something like this. Or we can even call this the bond polarity diagram. Okay. Now, when it comes to bonds, yes, the method is straightforward. We look at electronegativity values, we calculate the differences, and we see which category it falls into based on those numerical differences. Now, what happens if we have a compound where we want to know the entire polarity of the compound and there is more than one kind of bond at stake?